What's up guys? In today's video we'll be talking about recursive formulae in the topic of inductions. So we'll go through two examples. We'll start with the first one over here. So it's for the sequence defined recursively, t of n equals to t of n minus 1 plus 2 times n for all n greater than 1 where t of 1 equals to 2. Prove t of n equals to n squared plus n for all integers n greater than or equal to 1. Again, same thing, 3 steps. Start with the first one. Step 1. Let n equal to 1 in this case from here. Come over here. T of 1 should be 1 squared plus 1, which equals to 2. Therefore, true for n equals to 1, because t of 1 over here gives me 2 from the question. Step 2. Assume n equals to k. N equals to k to this, so this then becomes t of k. T of k equals to k squared plus k, because sub it into this. Now prove for n equals to k plus 1. Sub that into this again. So t of k plus 1 equals to k plus 1 all squared plus k plus 1. We get k squared plus 2k plus k plus 1 plus 1. So we get k squared plus 3k plus 2. So the value of, so this is what we're trying to find. This is what we're trying to prove is t of k plus 1 equals to k squared plus 3k plus 2. Now we come back to this first part that we've been given. Sub t of k plus 1 into this. So t of k plus 1 into this gives me equals to t of k plus 1 minus 1, 1 and 1 chop. So t of k plus 2 brackets k plus 1 in this case. Next step, we already know what t of k is from step 2, which will then give me k squared plus k plus 2k plus 1 in this case. Sorry, 2k plus 2, because when you expand the bracket you get 2 plus 2, which then finally gives me k squared plus 3k plus 2. Therefore, step 3, this equals to RHS. Therefore, step 3, through mathematical induction, through mathematical induction, it follows that step 1 and step 2 are true. Making true for all n greater than or equal to 1. So very, very simple, straightforward example for the first one. Now we'll go on to example number 2. Looking at this next example, we have 2 parts. So we'll start with A over here. So it says if it says if u to the r plus 1 equals to 2 u to r plus 1 for all positive integers r, prove u to the n plus 1 equals to 2 to the power of n minus 1 brackets u to the 1 plus 1. Same thing in induction, we'll go step 1, step 2, step 3. So for step 1, this time I'm going to take 2 values for n because it'll be more in a way relevant to the first part of this question. So let n equal to 1, sub it into this over here. We have u to the 1 plus 1 equals to LHS. Then RHS is going to be 2, 1 minus 1 is 0. We have 2 to the 0 brackets plus 1, which is just going to be u1 plus 1. Therefore, true for n equals to 1. So true for n equals to 1. Now we go n equals to 2. N equal to 2 in this case. Next step, LHS is u to the 2 plus 2, subbing 2 over here. RHS would be subbing 2 there, so we have 2 to the 1 brackets. We get u to the 1 plus 1 in this case. Next step, 2u to the 1 plus 2 over here. But what is 2u to the 1 equal to? This is also we can also write this as u to the 2 plus 2. So we can rewrite this as 2u to the 1 plus 2. Therefore, LHS equals to RHS. That is how you do step 1. Now we go on to step 2. So step 2, assume n equals to k. Assume n equals to k. Sub it into this first. So we have u to the k plus 1 equals to 2u to the k plus 1. And then sub it into here as well. So u to the k plus 1 equals to 2 to the k minus 1. We have u1 plus 1 right here. Now we go prove for k equals n equals to k plus 1. So prove for n equals to k plus 1. N equals to k plus 1. Sub that into this over here. So we have u to the k plus 1 equals to 2 to the power of k plus 1 minus 1 is just k. Brackets u of 1 plus 1. So that is what we're trying to prove over here. LHS equals to u to the k plus 1 plus 1. But we already developed this over here, which is 2u to the k plus 1. So let's sub that in. So we have 2 u to the k plus 1 in this case. Next step, so this we can rewrite this as 2u to the k plus 2. But u to the k, if we come back to this over here, we subtract 1 on the other side, we get u to the k. Correct? So sub that in over here. We then get let's not do that. Let's do this. Let's factor out 2 brackets u to the k plus 1. Yeah, there you go. Now we go 2 bracket. Now we don't have to bring the minus on this side. We can just sub this in over here. So we have 2k minus 1 brackets u to the 1 plus 1 in this case. 2 brackets here. Next step, simplify this over here, which then gives me 2 brackets 2 to the k multiplied by 2 to the power of negative 1, which is 1 upon 2, so 1 there, u to the 1 plus 1. In this case, 2 and 2 chop off, so then gives me 2 to the k brackets u1 plus 1, which is the RHS. Goes to RHS. That is how you do step 2. Now we're going to step 3. So step 3, we have by mathematical induction, it is true for n equals to k plus 1 if n equals to k, hence true for all n greater than or equal to 1. So that is how you do question A. Now we're going to B. The first step I will do in order to solve B is rewrite u of r. So in the previous example, we'd found that u of r plus 1 equals to 2 to the r minus 1. We had u of 1 plus 1, correct? Minus 1 from both sides, we get u of r equals to 2 to the r minus 1. We have, but it says if u of 1 equals to 1. So we have 2 brackets minus 1. So further simplify this, we get 2 of r upon 2 multiplied by 2 minus 1. 2 goes, you have 2 of r minus 1. Okay, let's sub this into this over here. So rewrite this, sigma n, we get r equals to 1. We have 2 of r minus 1. Further rewrite this as n r equals to 1. We have 2 of r minus n. Further simplify this, we can go 2 brackets, 2 of r, sorry, not 2 of r, 2 of n, minus 1, all upon 2 minus 1, minus n. Simplify this, we get 2n plus 1 minus 2 minus n, which should be the final answer for B. So, a little bit different recursive formulae, but it's a good practice to get our head around. So yeah, that is how you do these 2 examples.